All right, hi physics people. So I've got a little demonstration here for you, and this is going to hopefully help you understand a little bit better where the concept of electrical resistance comes from and how the different features of a wire factor into the formula. So I have a box full of air. I have this top with a foam piece that's meant to keep it a little bit rigid. And then inside the box, I have a plastic bag full of air. And this air is going to represent the electric charge that will flow through our conductors. Now, normally, the type of conductor that usually carries charge is some kind of metal wire, because it's carrying, the same way that water would flow through a pipe, electrical charge flows through metal wires because in metals the electrons are able to move around. And to represent those wires, I have a bunch of little plastic straws. I've got 5 straws, so let me show them to you. They have different lengths. Some are short, some are long. And they also have different widths. So the white straws are these skinny little regular drinking straws. And then the colored straws are these thick straws that you might drink a milkshake through, or bubble tea if you like bubble tea. And then I also have this one straw that I have filled with cotton stuff. So the rest of the straws just have air inside, but this one has sort of cotton stuff inside. And the 3 things that go into the formula for resistance are length, cross-sectional area, and resistivity. So here's our sort of reservoir of electric charge, and we're going to see what it's like to flow through these different wires. So the first variable that I want to investigate is the cross-sectional area. So if we compare straw number 2 and straw number 3, they're the same length. They both have just air inside. What's different is basically the area of this circle that the air has to flow through. So the cross-sectional area is just a more specific way of talking about like how thick is it. So we have this thicker straw, that's number 2, and we have this thinner straw, that's number 3. So I want you to think about, either from your own gut feeling or from the formula, which of these 2 straws is going to have a higher resistance. And I'm actually going to try it out. So I've got my box full of air. I'm going to see how hard is it to push out the air through each of these straws. So on the corner of the box, I've been holding it closed. I have this little plastic, the corner of the plastic bag has a hole in it. And I'll sort of attach each straw to the plastic bag, and then I will push down on the top of the box and see how easy is it to push the air out through straw number 2 or through straw number 3. And I'll tell you from my subjective sort of experience here pushing on this, it definitely feels more difficult to push the top of the box down, to push the air out through straw number 3 here. And I could do the same comparison, again keeping everything else constant when I'm comparing things, with straw number 4 and straw number 5. So predict again which of these straws is going to have a higher resistance. I'll try straw number 4. a long and skinny straw. Might be able to hear the air hissing out there. And I'll also try straw number 5. If we were in class, I'd have different people trying it out and comparing. Yeah, it's definitely easier to push the air out through straw number 5, more difficult to push it out through number 4. So we would say that number 4 has a higher resistance. So if we increase the cross-sectional area, that decreases the resistance, or if we decrease the cross-sectional area with the small straw, that increases the resistance. So we could say that's an inverse relationship, because when you increase one thing, it causes the other one to decrease, and vice versa. Okay, now let's talk about length. So, still got some air there. So for length, let's compare straw number 3 with straw number 4. Everything about these two straws is the same, except that they have different lengths. So make a prediction about which straw you think will have higher resistance. I'll try number 3 first. And then I'll try number 4. Number 3. I think I had it a little bit pinched the first time. Yeah, it's definitely somewhat easier to push the air out through number 3 than it is to push the air out through number 4. So a longer straw, or in terms of actual current, a longer wire, creates more resistance. Hopefully that makes intuitive sense. The last of the 3 variables that we're going to talk about is the resistivity. And the resistivity is represented by the cotton in this straw versus the empty straw here. In reality, any conductor that you have would have some amount of resistivity, because there's other stuff in the metal besides just electrons. If it was only electrons, it would fall apart. So there's other stuff in the way that's making it harder for the electrons to flow. And depending on how much of that there is, that's going to either increase or decrease the resistivity. So this is kind of an extreme example where there's nothing in this one. In reality, it would be less stuff in the way in one versus more stuff in the way in another. But we're using the cotton to represent the resistivity of the material. It's important to understand the resistivity doesn't depend on the length or the cross-sectional area. The resistivity describes a material. So for example, copper, aluminum, silver, each of those have their own sort of density of stuff in the way, their own resistivity. And you could make wires of different lengths and different thicknesses out of all those materials, and the total resistance at the end is related to the actual specific wire that you have. That would depend on the length, the cross-sectional area, and the material, which has a resistivity. So all 3 of those things would come together to create the resistance that describes a specific wire, whereas the resistivity describes a material you could make a wire out of. It's unfortunate that these words are so similar, but it is what it is. Okay, I actually think I need to put a little bit more air in here first before we're ready to test out straw number 2 versus straw number 1. So while I'm doing that, think about a prediction of which one's going to have higher resistance. I bet you can figure it out. All right, that's good enough. It's like halfway full, but that's fine for what we're doing. So I'm going to try straw number 1. See how much resistance there is to me flowing the air through the straw. It's pretty difficult. I can feel it takes a bit of work to push it down, and there's not that much air coming out. Versus if I compare to straw number 2, I can just push that right down, no trouble at all. I can feel the resistance a little bit, but it's much easier to push down. So higher resistivity was higher resistance. So again, we have a direct relationship. Increasing resistivity increases resistance. Increasing length increased resistance. And then the area was an inverse relationship. Increasing the area decreased the resistance. So in the formula for resistance, here's the resistance. Resistivity and length are both on the top, meaning they have a direct relationship. Increasing this number will increase the resistance. Increasing this number will increase the resistance. Versus the cross-sectional area down here, increasing this number will decrease the resistance because we're dividing by a bigger number. Okay, so if you had a big hunk of metal and you wanted to make the highest resistance that you could, you would want to think about what shape would you want to do to that metal. Would you want a thick, short wire, or would you want a really long, really thin wire in order to have the highest resistance possible? Okay, thanks for tuning in. I hope this helped you understand a little bit better, and I hope you're having a great week. Talk to you soon. Bye.